Hello everyone, I am Mr. Ish. Thank you for joining me. In this video, we're just looking at a comprehensive example, further revision of this concept on position, velocity, and acceleration, how you handle these questions using a calculus-based approach. Very quickly, just remember this. At any point you are given a position function, you can do the derivative of this and arrive at the velocity function, and you can go back by means of an integral. Whenever you have an acceleration function, if you are to take the integral of it, you end up at the velocity function. From the velocity function, you can do the derivative of this and end at the acceleration function. Keep also the concept of displacement, which is a net effect, and distance, which is a cumulative effect. You can have a net area develop over here with regards to the curve. You have negative and positive areas adding up to give you the net. With distance, everything is viewed in terms of a positive area. In the instances where you have no such thing as a negative area and everything is with regards to the area of the curve is all positive, then in that instance the displacement and the distance are the same. We will look at a comprehensive single example in this video and we'll try to make the most out of it. We have an acceleration function given. Acceleration regards to time is 2t plus 3 meters per second square. We have an initial velocity of minus 4 meters per second. We have a time interval there from 0 to 3 seconds. We have to find the velocity function. We have to find the velocity of this object at time 3 seconds, which is v3, and we have to find the distance and the displacement. You know we're given here the acceleration. If you are given the acceleration function and you do its integral, you know you're going to end up at the velocity function, and that's exactly how you should proceed. If you take this velocity function 2t plus 3 dt and you integrate it, the antiderivative will be 2t squared over 2 plus 3t, and you must add the fact that you have this initial velocity of minus 4, which is the velocity at time 0. You have a minus 4, and this right here represents your velocity function right here, 2t squared plus 3t minus 4 meters per second. We can simplify it out over here because we have something which cancels out. You have t squared plus 3t minus 4 meters per second, and this right here is the answer for number A. You must not forget to incorporate this into your velocity function. For the part where you are told to find v of 3, it's not hard at all. You just have to plug 3 in places of these t's. You'll have 3 squared plus 3 times 3 minus 4, and you can easily calculate it. You'll have an 18 minus 4. You have 14 meters per second. So for this object, given these parameters of 2t plus 3 representing the acceleration, the velocity function is this right here. We now know at time 3 seconds the speed of this object, or the velocity, is 14 meters per second. The velocity here is a better term than using the speed, because speed is a scalar quantity, velocity represents a vector. Now in the remainder of this video, short video, we'll answer question number B. You know the position function is given by the integral of the velocity function. If we were to do the integral of this, the antiderivative would lead us to this position function, and you can do it. But prior to that, we should do a graph of this, because we need to see if there's a distance and displacement coming into place over here, or will everything in terms of distance and displacement be equal to each other, because there will be no net effect coming into play. If you were to graph this function right here, t squared plus 3t minus 4, you can even factor it out. You have t plus 4 and t minus 1, and t here is equal to minus 4 comma 1. These give you your x-intercepts. If you take the same equation and you zero out t, you get a 0 comma minus 4. That gives you your y-intercept. If you do completing the square technique, you can easily do it. We don't have to actually spend time doing it, because I've already done it here on the side. If you were to do it, you would get, in terms of your vertex of this parabola, a minus 3 over 2 comma minus 25 over 4, if you did the completing by square technique for this. Given all of this, we have the ability over here now to generate a graph. We know the vertex here is minus 1.5 by minus 6.25. It'll be somewhere down over here. We know there's a y-intercept right here of 0 comma minus 4, 1, 2, 3, 4 right over here. We know one x-intercept is a 1 right here, and another x-intercept is a minus 4. By simply factoring this out, we've gotten our x-intercepts, and we can connect this over here and this. And we know our interval is from 0 to 3. So when we look at this area bounded by the curve with regards to the interval from 0 to 3, we can see there's a region below the curve and there's a region above the curve. So we now know very clearly here that we will have a net effect. That means the distance and the displacement items will not be the same. If there was no area here with regards to a negative area, everything was above this x-axis with regards to the curve, you would have a situation where the distance and the displacement are the same. But we can easily deal with this net effect by looking at the displacement first. We can see that if you do the integration, the definite integration from 0 to 3 of this function right here, t squared plus 3t minus 4 dt, which automatically has this positive and minus net effect built in. You know, when you're doing integration, you already have the net effect built in. You don't have to think extra. When you do the actual integration of this, you'll be seeing the displacement come out because it represents a curve which has an area above and an area below. When you do this, you get t cubed over 3 plus 3t squared over 2. Here's the integration of this, minus 4t. From upper limit 3 to 0, you plug in the 3's and you plug in the 0's, and the difference of that, 0 is meaningless, just plug in the 3, and here I end up getting 10.5. This 10.5 meters represents the answer for displacement. What this means is, from a position of 0, our object had a final resting place which was 10.5 meters to the right. That's what it means. But certainly the distance will not be the same answer as this. It must be larger than this. The fact that you had some negative area means that the object moved a little to the left, but more of the object moved to the right. Hence the net answer is a positive 10.5, meaning a 10.5 meter displacement to the right. What we have to do next is to calculate the distance. The distance will be viewed as simply from this interval of 0 up to this point right here. And what is this point right here? We know this point to be 1, 0. How do we know that? Because that was one of the x-intercepts. So from an interval of 0 to 1, what we have to do is pretend that this part of the curve is upwards. And we're looking at two areas which are positive, and we're just going to add them up. So let's do that. So the distance calculation will go this way. Let's just write distance here. It's going to go from 0 to 1. We have to bring in the absolute value of this function. We'll do t squared plus 3t minus 4, or you can just put a parenthesis, circular parenthesis with a minus outside, it's all the same, dt plus from 1 to the remainder of this interval from 1 up to 3, we'll capture the rest. This will be t squared plus 3t minus 4 dt. This does not require an absolute value parenthesis because this already represents an area which is positive. This requires the absolute value parentheses because this is a negative area. You have to do the integration of this. This, you know, will be t cubed over 3 plus 3t squared over 2 minus 4t, absolute value 1 and 0. Here you'll have t cubed over 3 plus 3t squared over 2 minus 4t. From 3 to 1, we have to publish these answers over here, and let's do them. In this area, from here, the calculation using interval of 1 to 0, I get a minus 2.166 repeating. Here, let's bring in this value. You have to put upper limit 3, lower limit 1, and the difference of the two with regards to this calculation. Here I get a 12.666. When we add these up, this will become a positive. We're doing 12.666 plus 2.166, and I get a total distance of 14.833 repeating meters. So you can see the stark difference between distance and displacement. The distance here is 14.833 meters. The displacement was 10.5 meters, but to the right. But this represents the total distance that the object has traveled using the parameters, and over 3 seconds, initial velocity of minus 4 meters per second, acceleration function of that, whether it was right or whether it was left, but the total distance traveled was this. And that right there, in a nutshell, in this comprehensive evaluation of this single question, shows you how we can use integral calculus to determine the velocity function and to determine the position function, from which you can clearly ascertain distance and displacement by means and aids of a graph, because the graph helps you see if there was a negative area. Without doing the graph, we may have done the calculation straight through from 0 to 3 and ended up with that value of 10.5, and we would have said then that 10.5 incorrectly is the distance, when in reality it was really the displacement. But by means of the graph, we know there was a negative area and the positive area, which clued us to the fact that in this case distance and displacement are two separate values and they both need to be ascertained. That's all I want to present with this video. I hope you enjoyed it. Thank you for watching. Have a nice day.